Programmer Mitch, hopping in today with another programming problem coming in. I'm just going to take one moment just to make sure that the stream is live. And that is my baby in the background if you can hear him. Hopefully he, yeah, we got it, good. Very good. Hopefully he doesn't try to help too much. Today's program, well, let's hop right into it, is Leetcode number 628, maximum product of three numbers. So given an integer array, find three numbers whose product is maximum and output the maximum product. Today, I'm going to try to do three ways to solve this, ending with the best, or my favorite, but all different approaches that have very interesting things, I think, to talk about. So as we spoke about before, we want to follow the paradigm of repeat, provide examples, then talk about the approach, then code, then test and optimize. So let's hop right into the examples. So the examples here for just the 1, 2, 3 array, it's 1 times 2 times 3 is 6. If we provide an input of 1, 2, 3, 4, then we are going to get 24. So we're going to take 2 times 3 times 4. We also have a couple notes. The length of the given array will be in the range 3 to 10 to the 4th, and all elements are in the range minus 1,000 to 1,000, and multiplication won't exceed any 32-bit signed integer. Okay, so let's think about this problem. And the first solution I'm going to do is, I think, interview cake's preferred solution. To get the maximum product of 3, well, let's go to the big board. If we have 1, 2, 3, 4, and we add another element of minus 5, well, that's not going to change anything, is it? Our maximum product of 3 is still going to be 2 times 3 times 4, which is 24. But if we add a minus 6, and this is a big hint for ways to solve this problem, then it does change things, because we want to use the 5 times the 6, and that times the 4. So we have a new answer of 30 times 4, which is, what is that, 120. Hey guys. Hey, pulsating mustache. Hey, Quote Eli. Welcome to the stream. So the main idea behind this is we want to not only to find the highest product of 3, or maximum product of 3 numbers. We want to keep track of the highest product of 2 numbers and the minimum product of 2 numbers. So the lowest number that could be possible. That's simply because a negative number times a negative number is a positive number, and that could kind of flip where we're looking. To keep track of the highest product of 2 numbers and the lowest product of 2 numbers, well, we need to also have a running max, and so that and a running min. So that informs where we're going from with the solution. So with that, I'm going to hop into this somewhat lengthy interview cake solution. So, like we said, we're going to instantiate, a highest product of 3, which is going to be just simply the first 3 elements in the array times each other. To instantiate the highest product of 2, that's going to be just the first 2 elements multiplied by each other, because we're going to be, when we do a for loop, we're going to be starting at the third element, which is 2. Then so we have the lowest product of 2. That's also going to be nums of 0 times nums of 1. Oops. And then we have the highest max, we'll call it. This naming is not great, but we'll roll with it. And that's just going to be nums of 0 and nums of 1. The highest min is going to be very similar. That's just the min of the first 2 numbers in the list, Python list or array in other languages. So we start our for loop for n in, as promised, starting from the third element, which is 2, because lists in Python are 0 indexed. And then we just kind of do like a waterfall. What we say is the highest product of 3 is just going to be the max of what it was, the current number that we're looking at times the highest product of 2, or the current number we're looking at in the lowest product of 2. Yeah, and then we're gonna redefine or reassign all those numbers as well. So let's get right to it. This is a very verbose solution, and we're gonna make some improvements on that later. But like we said, it's the max of the highest product of 3, and n times the highest product of 2, and also n times the lowest product of 2. Then, similarly, we have to think about what the highest product of 2 is now. That's just the max of the highest product of 2. This is a lot of typing, now that I think about it. And n times the highest max, and also n times the highest, excuse me, I don't want to call this the highest min. That doesn't make a lot of sense. I want to call this the lowest min. You may be hearing a baby crying in the background, which makes solving this algorithm a little bit more difficult. Hopefully you don't have that at your work. The lowest product of 2, it looks very similar, and to the point where I'm actually going to copy this line, so I don't have to write everything again. So now we have the lowest product of 2 equals not the max, but the min of the lowest product of 2, n times the highest max, n times the lowest min. Those stay the same. And then we think about, okay, what's the highest max as we walk through this array? And that'll be the max of the highest max, or the current number that we're looking at, also known as n. And then we have the lowest min equals this. Equals the min of the lowest min and n. And then we just simply return the highest, simply because this is pretty verbose, the highest product of 3. So how are we doing for time? About 7 minutes. And the purpose of time, oh yeah, so it's very important that the highest product of 3 leads, and then it falls down in this order. If you reverse the order, I'll leave that not as an exercise to the reader. I'll just tell you, you don't want to assign your lowest mins because they kind of feed up into it. You don't get the correct solution if you do your lowest mins and their highest product of 2 and then your highest product of 3. You need to have the highest product of 3 first, which uses the highest product of 2, basically from the previous time you walk through the array. Let's go ahead and submit this solution after doing a quick run through. And everything seems to be in order. So let's see if we pass. And I don't have a lot of time for debugging this one because we're going to do 3 solutions, so it's a good thing that did. So this is accepted. The time complexity for this is linear. Time complexity, this is O of n, because we're just walking through the array or list once. And the space complexity is constant time space. We're not storing a lot of things in memory. But if we look at the more details, we'll see that we're here. Our runtime beats 2% of Python submissions, so about 300 milliseconds. So pretty dang slow. So let's see if we can improve upon that. And let's go back. So let's go to the big board after we erase everything. And take a step back and think about the problem after taking a drink of water. So if we think about this, the highest product of 3 can only really be 2 different things that we have to compare. One, it could be the largest number in a list or array in most languages times the second largest times the third largest. So it's the largest times the second largest times the third largest. Or because 2 negative numbers multiplied by each other make a positive number, it could also be the largest number times the smallest number times the second smallest number. So that's all we really have to care about. So one way to get at what is the largest number, what is the smallest number, is to just go ahead and pop in and sort the array. So we saw this big nasty mess, which I've already deleted, which was linear time complexity. But there's a lot of maxes, there's a lot of calculations as we're doing this linear time complexity, as we're walking through this. So if we go ahead and delete that, and actually sort this, which is n log n. So we destructively sort. So when you do nums.sort and call it like that, nums becomes itself sorted by default from lowest to smallest. Then all we have to do is return those things that we talked about. So you just have to return the largest number, which in Python, which is in this case the last number in this list in Python, or this last number in this array. And in Python, you just do nums of -1, which is great. That's the last element in a list. And what to do is times the second to last element times the third to last element. Similarly, that's nums -2 times nums -3. So we also wanted to compare that max between the largest number times the second largest number times the third largest number with the largest number times the smallest number times the second smallest number, in case those were negative. So let's go ahead and do that. That's nums of -1. And then the smallest number in a sorted list from least to greatest is the 0th element. And that is then multiplied by the first element. So that's it. And so this is time complexity of n log n, and the sort is the space complexity of log n. But if we just submit this solution, what we'll see is, one, it's accepted. It's not very long, and it's not a very complex algorithm, which is nice. But if we go to more details, we'll see we're beating about 44% of Python submissions. So a lot of people, when they're getting used to big O notation or thinking about time complexities, like, well, how is that possible? How do we have this solution is O of n log n, right? The previous solution that we showed was O of n, but here we're showing that, and I'm going to resubmit that. The previous solution was 300 milliseconds, and now this solution was, I believe, around, we rerun it 48%. It differs whatever we find the state of the server in. This solution is a little bit over 100 milliseconds. So a lot of people, when they're getting used to time complexity, like, well, how is that possible? Well, time complexity only tells you as your input grows how much more time is it going to take to process. So in the previous case of where we had time complexity of O of n, if we doubled our input, what we're going to get is it's going to take twice as long. In this case, it's not going to take more than twice as long with this sorting algorithm. It's going to take 2 times log of 2 long. But that doesn't mean that things that are linear time complexity are necessarily faster than n log n or things of that nature. It all depends on like how many calculations you're doing, and you saw in the previous code that there was quite a bit of calculations. Let's see if we can get this even faster. Let's see if we can do linear time complexity with the constant time space complexity. So time complexity of a notation of O of n and space complexity of O1. With that thinking with the largest, the second largest, and the third largest, keeping track of those, as well as the smallest min and the second min. And so one way to do that is to, first take a drink of water as my throat gets a little parched here. But one way to do that is to kind of have a waterfall. So this one I'm not going to go to the board, but I will go to the big screen. If we have a number, if we're keeping a running track of the third largest number, the second largest number, and the first largest number, and we have a new largest number, what happens? Well, the number that was, actually I will go to the board. So let's say we have a max 1, which is the big daddy, the big king here. Then we have a max 2. And then we have a max 3. Can I see that? Yes. So what happens if there's if we're looking at a number n, and that is bigger than the max 1? Well, everything kind of shuffles down. What was max 2 is now max 3. What was max 2 is now max 1. And max 1 is n. You have to be careful how you think about this without overwriting stuff. But that's the gist of it. Now let's move that n to be bigger than the max 2, but it's now smaller than the max 1. So what happens? Well, same thing, except we have one less step. The max 3 still becomes max 2, but the max 2 now becomes that n. Max 1 doesn't become n, it's not involved in this scenario. Similarly, and the last thing that we're going to be concerned with in this example, if n is just greater than the max 3, then just the max 3 becomes the n. And then you're done with it. You can very similarly think about this with min 1 and min 2. Same exact process. So with that, with the time complexity of O of n, just walking through the list or walking through the array, we can keep track of our third largest, second largest, first smallest, and second smallest, and then just return the exact same type of return that we see here. So let's go ahead and do that. It's kind of like a waterfall. Things kind of bump things down. So we got about 14 minutes, got plenty of time. So what we're going to do now is we're going to instantiate the mins to be the largest numbers that we can show for this problem, and then the maxes to be the smallest numbers, the most negative. And then we're going to overwrite those as we walk through the list. A lot of times I don't like doing this. I like to use elements in the list, but for the sake of brevity, and I think it works well in this case, we're going to go ahead and do that. So min 1 is going to be the same as min 2, and that's going to be, this is the largest number that we can show for the purposes of this. It's just a max int, so it's like 2 to the 32, I think. And then max 1 is similar. Not quite that. But I'm going to keep on going for the time being. Max 1, the first largest, and the second largest, and the third largest, is going to be the negative of system max int minus 1. So those are the minimums are the biggest numbers, and the maximums are the smallest numbers, so those are going to be overwritten very, very quickly. So we just say for n in nums, if n is greater than, and we just code that waterfall that we did there. If n is greater than or equal to the max 1, the biggest number, well, to prevent overriding, we kind of go from the bottom up. So we say, well, nums of 3 equals nums of 2. Nums of 2 then becomes nums of 1, and nums of 1 is the n. And it kind of bubbles up. And when I say nums here, I mean maxes. So max of 3 becomes max of 2. Max of 2 becomes max of 1, what the previous largest number was, and then the max of 1 becomes n. Similarly, if n is greater than or equal to the max of 2, the second largest number, well, then the third largest number becomes the second largest number, and the second largest number becomes whatever number we're looking at. And I think we'll probably do elifs here. That'll be a little bit better. And then if the last case where the current number that we're looking at is greater than the max of 3, the third largest number, well, then we just reset the third largest number to whatever we're looking at. Now, I'm going to take a drink. And we're also going to show the negatives. So if n is less than or equal to the min of 1, same idea. Then the second largest smallest number becomes whatever the previous smallest number was, and the previous smallest number becomes whatever we're looking at. And if n is only less than the second smallest number, then we just reassign that second smallest number. Then at the end of the day, we return the max of the first biggest number times the second biggest number times the third biggest number, compared to the first biggest number times the first smallest number times the second smallest number. So that will be max 1 times max 2 times max 3, and max 1 times min 1 times min 2. Let's take a quick stroll through the code before testing it. We instantiate our mins to be the biggest numbers possible, the maxes to be the smallest numbers possible, so we can overwrite those. We walk through the list, and we have that kind of waterfall, which I'm just going to double check that everything looks correct here. And everything appears to be on the up and up, so let's go ahead and submit the solution. And we have a little bit of time to debug if we still have some problems. And we get a wrong answer. So 960 times 720. So we don't have a ton of time. I may have to go to some solutions first, but let's see if we can debug this. So min 1 equals min 2 system max n. So we have an output of 960. We have an expected output of only 720. I'm not just kind of looking through the input and seeing what the error for that would be. So 4 times 3 times 2, that's 6, 24. I'm not entirely sure what's going on in here, so I'm going to go through my code to see what the issue is. If n is greater than or equal to, that's sometime a catch here, but we do want to use the greater than or equal to because we want to bump that down. If we see the highest number is 5, what we've seen so far, we have another 5, we want to bump that down again. So max 3 equals max 2, max 2 equals max 1, and then max 1 equals n. If n is greater than or equal to max 2, max 3 equals max 2, and then max 2 equals n. If n is greater than or equal to max 3, then max 3 is greater than it. Excuse me, max 3 becomes n. If n, oh geez, not min 1 becomes n. Ooh, but let's go ahead and so that last one, the min 2 doesn't become. If you have a number that's smaller than the second smallest number, then the second smallest number becomes that number that you're looking at, not what the smallest number was. So why did that give us 960? 4 times 16. Yeah, so basically that overwrote. We had 2 minus 4s in that case, so 16 times 60, which I believe is 960. So that was why we had that mistake there too. So hopefully when we submit it now, we get an accepted solution, which is good. And although this is the same time complexity as the first solution we showed, it is way faster. Just about 100 milliseconds, faster than 95%, almost 95% of Python solutions. So this goes to show you that things that are in the same regime of time complexity for big O notation, in this case linear time complexity or O of n, they can be vastly different actual runtime speeds. Oh, runtime 79 milliseconds, so I should have seen that there. So yeah, this was the maximum product of 3 numbers. A nice little Leetcode easy, but I think it was just fun to kind of walk through 3 different ways to do it. And I think this solution is the best for this problem, or at least the fastest. The first solution I don't think is really good for anything. The second solution is the most terse, the one that's sorted. With that said, this is Programmer Mitch. We've got a little bit of time left, so I'm going to kind of show off. I've been watching First We Feast, which has hot ones. This is Da Bomb Beyond Insanity sauce at 135,600 Scoville. So I've kind of been following them and trying to build up my hot sauce tolerance. So I'm gonna have a little dab here as I exit out of the little program here. It's kind of a little jackass moment for you. Ooh, that is quite a big dab. So we'll see. This is going to be painful. This is quite a bit hotter than the Blair's original death sauce. So until next time, this is Programmer Mitch, and I'll catch you later. And I can tell I'm going to be feeling that. Ooh, baby. That is hot. Catch you next Sunday at 6:30 p.m. Ooh.